7, radians, arcs and sectors. So in the past you've learned about arcs and sectors. We talked about it very briefly last lesson, but we'll talk about it in more detail. In this lesson we need to learn about radians, which is something new for you, and also how do you calculate arcs and sectors if your numbers are given to you in radians instead of degrees. So in math, so far, for the last many years, we've been using the unit of D for angles. Degrees, yep. So you might have learned a little bit about radians in GCSE, but it wasn't part of the course formally. So if you weren't taught about radians, that's because it wasn't part of GCSE. It's just another way, like you know how sometimes we can measure length in centimetres or inches. Similarly, you can measure angles in like degrees or radians. There's other ones too, there's other units that exist. There's one called gradians, there's one called angular mil, but the one we're focusing on today, which is part of our course, is radians. Yeah, so remember when you go into your calculator, in your little calculators, if you go on and then you go to mode, remember there's two options, there's radians and there's degrees. So if you were doing just IB studies, math studies, you would only always be in degrees. But sometimes if you're in SL or HL, sometimes you need to switch between radians or degrees depending what the question's about. Like, is the question giving you the angle in radians or is it giving you the angle in degrees? So that's the extra challenge that you guys have. So you need to first of all understand what is a radian compared with a degree. How many degrees are there in a full circle? 360, good. How many degrees are there in a half circle? 180. So why are, first of all, radians? Radians are considered to be more mathematically intuitive or more mathematically superior as a way of measuring angles instead of degrees, and we'll try to show you why. Why radians are considered a bit more mathematically intuitive. Okay, sorry. Radians. So radians are more related to circles in that a full 360 degree angle is equal to 2 pi radian. So this is a nice little conversion. A whole 360 degree in a whole circle, a full turn in degrees is measured as being 360. If it's measured in radians, a full turn is 2 pi. How much is pi approximately as a number? 3.14, yeah. Yeah. I didn't know you could do that. That's impressive. So a 2 pi radians would be, so a full turn would be, what's it roughly twice pi equal to approximately? 6.28. Yeah, like 6.28, blah, blah, blah. So, what's that, Katie? Yeah, sure thing, yeah. Okay, so if you're talking about degrees, a full turn would be 360 degrees. If you're talking about radians, 2 pi radians is a full turn. So in a whole circle, there are 2 pi radians. So what I tend to use, you could just remember a full turn, 360 degrees is the same as 2 pi radians. I tend to use this conversion now. I tend to use pi radians equals, yeah, that's just my way I've always remembered since I was a kid. I just remember that pi radians is equal to a half circle. So like approximately 3.1415 ... radians is equal to 180 degrees. I tend to use this as my reference. To me, this is a super helpful reference. But if ever I'm in doubt of how to convert from radians to degrees, I have that as my reference point. And I use that to then convert measures from between degrees and radians. So you've already mentioned this. Recall what is pi approximately equal to as a regular number? Around about 3.14. You can put more if you want. If you like, 3.14. So trying to just point out how big roughly a radian would be. A degree is a tiny amount. Don't draw this. A degree is just a tiny little angle, isn't it? Whereas a radian is a bit bigger. So just to give you an idea of roughly how big a radian is, let's first of all draw a diameter. So diameter just means draw a line across the middle. Could be going down that way, so long as it passes through the approximate centre. And then try to divide 1/2, I'll do the top half, you can do the bottom if you want, of the circle into approximately 3.14 radians, just to get an idea of how big 1 radian would be. So it means split this into just a little bit more than 3. So it's got a tiny little bit left over, which is the 0.14, and then 3 equal bits, isn't there? I have to do on this dodgy board. So there'll be a tiny, tiny amount, which is like the 0.14.
Wait, why are we doing this?
Just to give you a vague idea how big a radian is. Like a degree is a tiny, tiny amount, like super small, isn't it?
Yeah.
Yeah, whereas a radian is almost like a third of
Okay.
half. Yeah, just trying to point out that in a half circle, there are 3.14 radians. So see, like 1, 2, 3 roughly equal sizes, and then a little bit left over, which is the 0.14. So this little bit, just need to point out, is the 0.14, and that one could be.
Wait, so you said that in 1/2 there are 3.14 radians?
Yeah, in 1/2, yeah, exactly. There are 3.14 radians. So there's 1 radian in, that I've done in purple. These 3, purple, this red one, and I'll do a yellow one, are meant to be all equal. Just trying to give you a rough idea of how big 1 radian is. So 1 radian is about meant to be the size of one of these. 1 radian is to be about that size. Each of those 3 are meant to represent 1 radian, and this little tiny sliver on the side is meant to be the 0.14. Because remember, pi radians equals 180 degrees. So I just measured in a 180 degree angle and tried to split it into 1, 2, 3.14 spots. So a radian is almost a third of a half circle. Just to give you an idea, a degree is a tiny, tiny amount, whereas a radian is a bigger slice of a circle. And the reason why radians is considered a bit more intuitive is because radians deals with the number pi, and pi is a special number related to circles. Because remember, how is pi calculated? What's the definition of pi? Yeah, pi equals the circumference of any circle divided by its diameter. So don't worry, this is not something you're meant to realise. Just trying to point out why circumference divided by diameter. Why radians are considered a bit more mathematically good to use than degrees. It's because they deal with the number pi. We kind of tend to talk of radians as being in terms of the number pi. And the pi has a special connection to a circle because pi is the circumference of any circle divided by its diameter. So that's just the only reason why mathematically radians are considered the better way to measure angles. But in the real world, we use degrees more. It just turns out in the real world, degrees became the most common way to measure angles. But radians is seen as the more mathly way to measure angles. But it's weird when you've grown up all your life using degrees. It's weird for you suddenly now to switch to the idea of radians. That's why I wanted you to see just roughly how big a radian would be. Okay, so that's that little thing there. What's that? Yeah?
I don't understand that, but I don't even know why I don't understand it. So like,
It's a lot to take in.
so like 1 radian.
Yeah.
So how did you even get to that? When you said that
Yeah.
pi radian is 180 degrees, right?
Yeah.
So when you saw 180, you automatically thought a half of a circle.
Yeah.
Why you went 1/2?
Yeah.
So now how did you go from there to
3 bits.
yeah?
Yeah, because pi
Yeah.
is equal to approximately 3.14.
Yeah.
So if you turned, instead of saying pi radians, you just said 3.1415 radians.
Okay.
So a half circle is equal to roughly 3.14 radians.
Radians.
Yeah.
Okay.
So then I just tried to divide it into approximately three equal bits plus a little 0.14 left over, just to show you roughly how big a radian is.
Okay.
Just because a degree is a tiny, tiny amount, isn't it? Whereas 1 radian is actually quite a big chunk of a circle. That was just so you could visually grasp how big a radian is roughly. That's all it was for. Yes, Bella?
Can I just tell you a math joke?
Yes, please.
Dude, why is a pie like shaped like a square?
Because it ate something, no?
Because pi are squared.
You guys get it?
What's the mathematician's favorite food?
Oh, I get it now.
Pie? I don't get Bella's one though.
What's the answer again? Coleslaw.
Coleslaw.
I like some good sport.
Grace, I don't get Bella's joke. Hi. So why was the question?
Pies aren't square because pies
Because
aren't
why-
square.
Why should a pie be actually like a square? Because pie are square.
Well, you didn't
Oh,
say
they
that.
are,
Why
ARE.
You said why are pies square?
Pi, ARE is squared. Oh, I get it. Thank
Pies
you.
are squared.
I think
That
it's
is
60. Walk right, people, please.
Thank you. Kieja's getting impatient, understandably. Okay, so use the general conversion in purple above to work out how many degrees would be in one of these radians. Like that's what we're trying to work out. How many degrees would be in one of these radians if pi radians is 180 degrees. So what I tend to do is, this is my little way. I write out my little general thing. I go pi radians. Sometimes we call them rad. That's just a short way for radians is rad. Pi radians equals 180 degrees. So I use a ratio idea. So pi radian, that's my general reference. Pi radians is 180. So 1 radian, which is what they wanted us to know, 1 radian equals x degrees, because we want to know how many degrees would 1 radian be. And then I tend to do this cross multiply thing. So that's my
Should
general
you write
reference.
pi word?
Why don't you just do 180 divided by 3?
So pi over 1 must equal 180 over x. See, I did that divided by that.
Oh,
Put
very like
that
a
over
ratio
that.
sort of thing?
Yeah, and then I cross multiply it. I tend to find, like, if I'm really lost, I just write this out, and then I write the thing I know, and it's the unknown, and then I do that divided by that equals purple over purple, and then cross multiply.
So why didn't you write pi again? So pi x equals 180.
Oh, because it said in 1 radian.
Pi
X, yeah, good, exactly, like Grace said. Cross multiply, pi x, or x pi, whatever,
So
equals
x
180.
equals 180 divided by pi.
Yes, exactly, and that's my answer. 180 divided by pi, and it was degrees is my unit.
So like if you're trying to find 5
Yeah.
degrees, you would multiply that by 5.
Yeah, exactly.
180 over pi times 5.
I do pi over 5 equals 180 over x, and then cross multiply again and solve. I just find like then I'm not getting too confused and muddled if I just have this, my general reference line, and then have the unknowns. Like make sure you've got degrees under degrees and radians on radians. Then you can turn them into a little fraction and cross multiply. I just find that way is my foolproof method, because you can get confused trying to think in your head, hang on, what do I divide by this, do I times by that? If I just set up these little reference equations, I just cross multiply and I'll get the right answer. That's called an exact answer. So 180 divided by pi would be considered an exact answer. If you were asked to round to 3 sig figs, you would just work out what's 180 divided by pi, and that's going to give you something like 57. Yeah, or 57.29. That equals 57.3 degrees to 3 sig figs. So there you go, that makes sense. According to our picture above, a little slice, the little radians that I drew up there, they're around about 57 degrees. So 1 radian is around 50.3 degrees. That's a rounded answer. An exact answer would be 180 over pi.
Was it ever tell you in a question to convert your answer to?
Yeah, and I've got a few questions later on the examples where the answer is going to be in radians, and then we're going to convert it to degrees. And it can be really confusing to do that, so I find this method, have my little reference, if I can just remember this purple reference line, and put the unknown degrees here and the known radians there, set up 2 fractions and cross multiply, then I don't have to think as much. I found I'm less likely to get confused that way. That's my little way. You might have your own way of rationalising it.
How come?
Because see, it does make sense. That's about 1 radian's about 57 degrees, isn't it? Yep.
So how come you didn't do pi times 1? Why did you pi divide by 1?
Oh yes, I'm kind of like setting up ratios. If pi radians is 180 degrees,
Yeah.
1 radian is going to be 1 pi times 180. As in, like, to go from radians to 1, because this is, notice this is radians. That might be confusing you. See 1 radian?
Yeah.
So I've got radians on radians, degrees on degrees.
Oh!
I've set up sort of two, that might help if I've got those, if you can see I've got the units in there. Pi radians. So turning from pi radians to 1 radian, I had to divide by pi. So similarly, to go from here to here, I'll have to divide by pi as well.
I think you meant divided by itself.
Yeah, but eventually I did. Yeah, see I did that. So rather than thinking of it like that, I just set them up as this, the purple over the blue, see purple over the blue, and then I cross multiplied, which eventually led me to dividing by pi. Then I'm not having to think so much. If I just set up these reference equations, radians on radians, write them then as a fraction over fraction, purple over blue, then cross multiply. And then I solve, and then I find I get less errors that way, get less confused. Puzzling, hey? And if you kind of, that's why I wanted to visualize. Yeah, because it said, use a general conversion, find the number of degrees in 1 radian. Yeah, so overall we're saying that 1 radian equals this as an exact answer, or this as a rounded answer, 360.
We just put X.
Yeah, so each of these answers is what 1 radian equals. And it does make sense, it's good to realise. So you realise that roughly 1 radian is about 57.3 degrees. So that way you know roughly, okay, if 1 radian is about that much, it makes sense. Because you can see from here, that's about 57 degrees. If I had a number like 210 degrees, I'd know something had gone wrong. Because we know a radian should just be a bit more like, you know, a third of half, just a bit less than a third of half of a circle. Confuzzling when you first hear this stuff. So we're going to convert the following convert the following degrees in blue to radians and give exact answers. I'll show you what I love to do. I love to write out my reference. Pi radians equals 180 degrees. I have my little reference. That's my little thing that I always go back to because that's easy to remember. Pi radians is 180 degrees. You can set up your little references. You can go pi over x. I'll show you if you do it with the reference. You would do pi over x because we want to know how many radians this time. So pi over x equals 180 over 90, wouldn't we? See, we've got radians on degrees. That's the way I set it up. So long as you've got radians, sorry, like, you know, reference 1 on the top, the unknown on the bottom, or vice versa. That's 90. And then you can cross multiply and solve. So 90 pi equals 180x. So x must be equal to 90 pi over 180. And 90 pi over 180, what does that simplify to?
90
Yeah, pi over 2. Pi over 2, and what's the radian? Rad is our x. Some of you might have just seen that. If pi radian is 180 degrees, 90 degrees must be half of that. Because see, 90 degrees is half of this. So half of pi is just pi over 2. So if you're in doubt, you can use this reference equation and cross multiply. But if you see automatically, okay, 90 degrees is half of that, 180 degrees. So in radians, that must be pi over 2, 1/2 of pi. So similarly, let's have a look at writing that so that you think of that first. 60 degrees.
So this is just going to be pi over 3 then?
Yeah, exactly. So see, you're starting to see a little bit of a pattern. Ones like this are just nice and easy to look at sometimes too. Pi over 3 is our answer. Oh, and don't forget to write rad. You can write the whole word radians if you want, but rad is the minimum. That's rad, not QD. So yeah, if you realise automatically, you see 60 degrees, it's just a third of 180. So as radians, that must be pi over 3, a third of pi. A third, you could write a third pi, or pi over 3 is the most basic way to write it. And in a similar way, what would 30 degrees be in terms of radians? Yeah, exactly. Because it's like 180 over 6 is 30 degrees. So pi over 6. And if they're not nice numbers where you can easily see it's 180 divided by something, you could use this reference idea and cross multiply. That will work as well. 45 degrees, anyone know what that would be as a fraction of 180?
Pi over 4.
Yeah, pi over 4.
Yep.
If you take 180, divide by 4, you'll get 45. So pi over 4 rad. It's fine if you see it, you can just go straight to writing it. Because you'll start to see some that you're familiar with, like 60s, 90s, 30s, 45s. 270 degrees is what fraction of a whole circle? Close?
1.5.
1.5, yeah. Yeah, so you could write 1.5 radians, because 270 degrees, it's 3/4 of a whole circle, isn't it? So you could say 1.5 radians, because pi radians is 1.5 pi radians, or 3/2 pi radians. So 1.5 pi, don't forget to write pi as well. Or you could write 3 pi over 2 rad. Just make sure you put the pi in there.
Wait, why do we, when we work it out, why do we write it as pi over x?
This one?
Yeah.
That was if you were doing the example, like if you didn't know 90 degrees, it's half of 180. You could do this referencing pi radians equals 180 degrees, see the purple over the purple, and we want to know what 90 degrees is in radians. I just didn't have much space to write out pi radians equals 180, x radians equals 90, and then set up the fraction. I didn't have much space to do that, so I just went straight to the fraction. Yes, Scarlett?
Unit circle for this as well.
Yeah, it's a little bit like the unit circle stuff, yeah. Unit circle is going to come back to haunt us. We do calculus, so it's good you're thinking of the unit circle. And a lot of the unit circle stuff, in the past we used degrees. So,
Are we going to learn the unit circle?
yeah, you're going to learn the unit circle again.
Like,
It kind
in
of,
this topic?
no, it goes with another one. You'll see unit circle is not in this chapter. We've just tried to stick to chapter by chapter. So this chapter just kept the unit circle out of it, whereas chapter 13, once we hit chapter 13, the unit circle is coming back to haunt us. And in the past we did the unit circle in terms of degrees only, but now radians, these kind of angles are going to appear in the unit circle a lot, once we get up to chapter 13 stuff. So that's kind of nice, because they're nice regular kind of like angles. Let's similarly convert the following radian measures to degrees. So as a little reference, I do like to write this out still. Pi radians equals 180 degrees. This helps me. If it doesn't help you, that's fine. That might help you to see the answer to the first one though. Or that one being degrees. Yeah, it goes, yeah, 180 degrees. Pi radians. This is 180 degrees. Interestingly, pi over 5 radians. If you had to show a little bit of working out, what could you do just as a basic one? Yeah, exactly. 180 divided by 5. Because pi is 180 degrees, pi radians, so pi over 5 radians will be just 180 over 5, which equals 36 degrees. 3.8 radians might be a bit more awkward. You might want to set up this fraction thing and cross multiply if you've got an awkward one like this. To you. So you could say, okay, pi radians equals 180 degrees over 3.8 radians. Radians over radians, degrees over degrees equals x degrees. So that's where this cross multiply business. We've not got a nice one like these ones. We've got an awkward number like 3.8 radians. Okay, pi radians is 180 over 3.8 radians, which is x degrees, and then cross multiply and solve. So then pi x is 180. Still got an awkward number. We might need to use a calculator for this one. So x equals 180 over 3.8 pi. It's an awkward number. So
Wait, why did you do 180?
yeah.
Why did you do divided by 3.8? Isn't multiply?
To solve for this, to solve for x.
Wait, because you're cross multiplying, right? Yeah.
Hang on, did I do something wrong?
You
That's it.
divide by multiply.
X pi times x. Oh, sorry, yeah, totally right. Sorry about that. That's awkward. Glad you are on the ball. Sorry about that. So, well, good. Okay, so pi x is fine, but it's 180 times 3.8. And then you could work out that first if you wanted to, and then divide by pi, or you could do it all in one big thing. Over pi, so your answers might pop out as a nice fraction. Do you want to try it on a calculator and see what you get for something like this? 180 times 3.8. 217.
217.7.
Yeah. So, yeah, you write down whatever answer you've got. So I've got 180 by 3.8. And no, remember you've got a nice little pi button here. Where's the pi button? There it is. So I just press second upward arrow to make a nice pi. I've got that. Math fraction. Let's see if it'll turn into anything nice. Math fraction. Oh, that's awkward. As in fraction, who cares about that? Okay, let's just write out the nice decimal answer. 217.72 blah blah. Is that what you got as well, Krista?
Yeah.
Okay, so it was...
And 218.
Oh, sorry, thank you, yeah, you're right. Because it would round up to 218, yeah. And it's degrees, isn't it? Yeah. So what are we doing? Yeah, so they're a bit more awkward, those ones. Because they're not just nice, simple ones like the first two. If we had to round to 3 sig figs, that's what we'd do there. 5 pi over 4 radians. Remember, pi radians equals 180.
So 180 times 5 divided by 4.
Yeah, exactly. You could just do 180 times 5 over 4. 5 over 4 times 180, yep. So give us a nice number. What's 180 divided by 4?
225.
225, nice number, yeah, good. So 225 degrees. 2.1 radians is going to be another awkward one again. Or it could be awkward like where we set it up like this.
Divided by 2.1 equals 180 over x.
Yeah. Pi divided by 2.1 equals 180 over x. I'm going to do 2.1 over 2.1 equals 180 over x. Yeah, remember radians over radians, degrees over degrees, plus multiply. So x 180 times 2.1. Is that one correct this time? What is that?
120.321.
3 Thank you. The 3 sig fault, it's hard to do exactly 3 sig.
120.
Okay, so that's the best we can do. So that's practice just converting between the two, which is awkward. Bit of an awkward thing to do when you're not used to it. Eventually you'll get very used to this. Like this will become like a second nature by the end of IB2. It's very weird the first time you see it. That was just basic converting. And then here's, so we've got 120 is the answer for the last one. Anyone still writing that down? It's a city in a country.
City?
Called Singapore. Isn't it?
Singapore is its own country.
I think so, yeah, and its own city.
Well, it's because in Crazy Rich Asians they said that Singapore, like,
I love that movie.
they went on a boat and they got to Singapore and it was this island jungle and then they turned it into this amazing
What movie are we?
Crazy Rich Asians.
Yeah.
Oh, I need to see that.
So
No, I need to see it. I need to see that movie.
Okay, so recall alert from the past. The past coming back to haunt us again. How would you, like sector area, here's a sector area in green. Arc length, here's an arc length. I'll just highlight it in yellow so you can see it. Oh gosh, I don't want that. What's going on here? Who's got the wacky pens on? Pen. Okay, that's what we want. So here's our arc length. That's what I was meaning by arc length. This length here. Calvino, I think you told us last lesson. How would you start to calculate the area, not of a whole circle, but of just a little sector if we knew that angle.
I was wrong.
Oh, you're right. Okay.
I asked for a 2 pi r, which one?
Theta over 360. That's the general way. Theta over 360 times. Yeah. Pi r squared. Yeah. Pi r squared is the area formula. So sector area would just be theta over 360 in the way we're used to it anyway, because we're used to degrees, times pi r squared. And arc length, if it was an arc length instead, very similar kind of formula. What would that be? Yeah, exactly, times 2 pi r. We use the second
Oh, that's some
formula.
type of remnants.
So that's if you're using degrees and you're asked to find a sector area or an arc length, you just keep using that lovely little formula that you know from the past. It's like, because it's what fraction of the circle is this area, it's the angle over 360. Same thing with that length there. Now let's see if we can come up with a formula if it was in terms of radians. So 360 degrees, it's the same thing. 360 degrees, if we were to do see the bottom one, they want you to use radians instead to come up with a similar set of formulas. And you'll find that they simplify to something really nice and simple. So so for the sector area with radians, I'm going to replace 360 degrees with 2 pi, yeah. And then you'll find it simplifies down to something nice. So sector area, because so you might just want to write as 360 degrees equals 2 pi radians. You might just want to put this down so you can look back and see why on earth have we got 2 pi underneath the angle. So you'd have theta over 2 pi instead, times by, actually you can use times instead, that's fine. Theta over 2 pi times by pi r squared. And same thing for this one, you would have theta over 2 pi times 2 pi r. But what's beautiful about using radians, yeah, they can cancel down a bit. Yeah. So you can come up with a nice simple formula, which if you were in a rush, you can simplify it. What cancels down here? Pi, yeah, so you can cancel out the pi, which would leave us with
Theta r squared.
yeah, half pi theta r squared or theta r squared over 2, yeah. Yeah, so you could say like Bella said, half r squared, no, half theta r squared. Yeah, half theta r squared is fine, or you can say theta r squared over 2. So either one's okay. Half theta r squared. Both are nice. Right, switch whichever one you like. Okay. There's only one of them that's compatible. What is this always happens to me? Okay. Sorry, about this. And then what's cancels down from 2 pi, yeah, so you can cancel out way more in this one. So that one, what is this? Theta r. Theta r, yeah. That's a lovely one. And I'm going to have to give you another copy of the front page of this notes booklet, because it turned out these formulas are also in the formula booklet, and I forgot to paste it on the, in the front page of your formula booklet, where it's got the picture. I can show it to you on here. I'll just open it on here, trig notes. Okay. See that? So this thing, I forgot to give you these ones. So I'll show you what's in the formula booklet. It's in your formula booklet anyway, so if you don't want a new copy, it's no biggie. Come on. Okay, alright, now everything's reacting, great. So these are the ones I forgot to give you. See length of an arc in terms of radians. Length of an arc is theta r. And the area of a sector, they use Bella's favourite version, half theta r squared. So they're given to you in your formula booklet. And I forgot to put that on the front page of on page 2 of your booklet. So feel free to just write it in if you want. Or I can give you a printout of it, another lesson too. That's also okay. Printout better? Yeah, I can replace the page for you. So they're the 2 lovely ones that are in your booklet. So let's maybe make a note. These are in your formula booklet. But they only apply when you're dealing with radians. So if you're dealing with degrees, use the original formulas that you remember from GCSE. If you're dealing with radians, you can use these lovely versions. These are in your formula booklet. That one and that one are in your lovely little formula booklet. So theta r, beautiful little formula for arc length. If you're dealing with radians, half theta r squared. Beautiful formula for dealing with sector area when you're talking about radians. So let's try to see how something like that could be nicely used here.
It would have been nice if these were 2 separate pages.
Yeah, it gives it more space.
It was nice to look at.
Oh, because then you could look. Yeah, you're right. It's annoying. Okay, so for an arc, which subtends, that's just a fancy way to say the arc comes from the angle. So for an arc, which is generated by the angle at the center of 125 degrees, the radius is 10, find the arc length and find the sector area. Notice, well, how have I given you my angle? Degrees? Sorry. Yeah. How have I given you the angle? Degrees or radians?
Degrees.
Degrees, yep. So would you use the nice simple version or will you use the traditional version?
Do we use the
traditional?
Yeah, I'd use the traditional version unless you really felt motivated to convert these to radians. But if you remember, I think putting it into the traditional version is better. So notice angle given in degrees. So use 125 over 360. And the radius they gave us, r equals 10. So arc length, it's just going to be 125 over 360 times, and its length, 2 pi r, 2 pi 10. And then you work out that lovely answer and then round it to 360. Sector area, you're going to do the same thing, 125 over 360, but times pi r squared, so times pi squared. Write your nice unrounded answer and then write your rounded answer. I'll give you a chance to throw them into a calculator. Let's see what wonderful things come from there. You must have a mathematical brain. I suppose everyone has a mathematical brain, don't they? It's just something. No. It's just like what degree of mathematics?
English, I don't have English.
You just write stuff.
Oh yeah,
English.
You just write stuff and read stuff. Is that what sounds hard in IB English is interpreting poems. That sounds difficult.
Well, that's what we've been doing all year.
But we never had to do that nowadays.
What?
No, we just had to interpret books and films, not poems. Poems are a bit more obscure. In my day, if you took literature as an extra subject, you had to interpret poems then. We just wrote about stuff. We'd always have there was some books that we had to read, and we had to write essays in exams about that book. Like there'd be a question about that book. I think you do that a bit in your IB exams too, don't you? No, you don't. There's not anything about your text that you read.
If you take higher English, you don't give a question.
Yeah.
You're just given a little snippet of something you haven't seen.
Oh, that's interesting.
And that's it.
Do you have to write essays about text then, and that gets submitted off like a journal assessment? Oh, so we had exams more like that, and every exam had to have every book that was possible. Like there's this list of books that are allowed, and we would read. Like normally you would assign 3 of them throughout the year, and so you could pick which one you wanted to do yours on. But there'd be 100 questions, and you just had to pick the one related to your book.
That's like GCSE.
Yeah, and we had to memorize quotes and all that kind of thing. Yeah.
That was GCSE.
Mm. But whereas you're given something you haven't seen, you have to interpret it, don't you? Aren't there certain universal themes, like something seems to always represent death? All these metaphors.
Not the soul we're doing today. It's just so selfish. I was like, because English, you reference it to death, survival, or war.
Or
And
love or
there's no
something like
reference to
that.
any of those things in this problem.
Love, is that
It's about
another one?
churning
Love's
butter.
probably another one.
Songs about churning butter.
Oh, they're all metaphors for something.
No.
Growing old, growing old at least, is that another classic thing?
You mean someone say English? Oh, that's best for you.
Or remembering as a child or something
Yeah,
like
it's
that?
remembering. Churning butter.
It's literally, yeah, just
It
checking
just
about.
tells you how to churn butter.
It's literally steps, like 4 steps of, well, 3 steps, and then what happens after you make it.
Have you learned yet what the meaning behind it is?
No, that's all.
No, we talked to her and she said it's just about churning butter.
Oh, it is literally about churning butter.
It's just a mere memory of him and his mother churning butter.
Churning some butter.
So
I
if
need
that
to
was
make
in
you
an
churn
exam,
butter.
you wouldn't get one like that in an exam though, would you?
Well, that's why she said, I have to give you hard ones, I have to challenge you.
But this one's our transcript one.
Exactly.
What does that mean?
That's the one that
It's-
Oh,
comes.
it goes on your grade.
I
Churning
need
butter.
those.
Meaning too fast. Okay, so what, I should write some numbers. What's the number? Sarah, you've always got a number.
21.8166, blah, blah, blah.
I love how many you can do. Okay, basically,
21.8
what kind of units?
M.
Oh, yeah, because it's a length, well done.
Yeah.
M, the length. 21.8 M. Sarah, what would be next for this thing?
109.08307, which is 109 and
Squared.
squared.
Yeah, that's right, good, because it's an area.
So
So that's a nice traditional question. It's good to still show you traditional questions. And then below though, we're giving you an angle in terms of radians. Ew. But what's nice is you can use, for arc length, you can use theta r, beautiful and simple formula, theta r. And for sector area, you can use theta r squared over 2. Did I? Yeah, just check that I gave you the right information too. Always good to check. Did I miss anything? So notice that this time, angle is in radians this time. In radians this time. So that means we can use a lovely formula in our booklet. The one, the traditional one that we used above, you have to memorize that, was that one in radians they give you in the booklet. In radians this time.
So I have to memorize
The one, the theta over 361. But that's a nice one to remember. But these ones for the new ones we're learning in this course for radians, if you forget it, that's fine. You can get it from the formula booklet. So radius is 4. So arc length, they call it L equals, what is it again? Can you remember?
Radius is half a diameter.
Yeah, half a diameter, yeah. So if I trick you and put in a diameter in the question, radius is just half the diameter. Arc length, can you remember the thing from the formula booklet? The nice simple one. Yes, lovely. Theta r. Isn't that wonderful? So you just put in 2.9 times 4. So radian, this is another good reason why things like this could be on non-calc. This could be a nice non-calc. What was it again? 30? Was it
11.6.
cm? Okay, good, yeah, because it's a length. Cm. So these are examples that could be on non-calc, because see, that's a lovely simple formula where you could just do non-calc. We could give you a radius of 10 or something, or 100. That could be done super nice on
And then
non-calc.
the next one is theta r
We
squared.
haven't even looked at it yet.
What do they,
The formula.
how did you write the formula? Did they call it
Theta r
GK?
squared over.
I had it on here, didn't I? And I just closed it again. Here it is in your formula booklet. They call it A. Sorry, I just thought I'd write the formula properly for you. So the theta, they go A equals a half theta r squared. Is that a lovely formula? Yep.
2.9.
Oh, you do 2.9 over 2? Yeah, totally, you can do that too. 2.9 and then, yeah. So you show, yeah, which equals
3.2 centimeters squared.
fabulous. We're getting nice numbers there too, aren't we? Nice. We didn't put the unrounded answer because there was no other unrounded answer. The answers just came out like that. So half theta r squared, or you could do theta over 2 r squared or theta r squared over 2. Same thing. As long as you somehow show a bit of working out, throw in the correct unit. Fabulous. It's 2:16. I've got just a few examples of some yuckier ones, which I could slightly yuckier ones, but that will take a little while. The last one?
Find the central angle pi and the radius r.
Exactly, yep. So notice, I'm not telling you to do anything, but this is a bit of a hard thing to do using degrees, so I'd suggest use radians. So let's try to find our answer in radians using the nice simple formulas, and then afterwards we'll convert to degrees, just because Part B asks it. Circle has a diameter. Find the size of the central angle subtended, meaning like which comes from an arc of length 30. So what is the formula in terms of radians for arc length again?
Equals to
Yeah, good. Theta R, yes. That's right. That's from the formula booklet. Maybe make a little note in case in a few days you forget where you got that from. From formula booklet. So it didn't ask for us to find our angle in radians or degrees. So let's do it in radians because that's a beautiful, simple formula to use. The radians formula is better. And they told us that the length is 30. We don't know the theta, but we know, they'll tell you. Oh, so good point. Oh, yeah, radius equals 10 if the diameter is 20. It's half, yeah, theta 10. So what's our angle got to be? 30 over 10. 3 rad, good. It's, because you're so used to degrees, you might go to right degrees by mistake, but if you're using the radians formula, it's 3 rad. 3 radians or...
Oh my goodness.
What's that?
Okay, I'm glad it's the end of the lesson. The pen stopped working. If I'm aggressive with it, sometimes it comes back to life. 3 rad. See, look, it just didn't work. Okay, so 3 rad. That's how you would find the angle. And then 3 radians, how would you then convert it to degrees? We could do that as a warm-up next lesson if you like. Because it's 3:18 now. So bring your little topic assignments tomorrow. I'll just close this. I think I'll make McDonald.